So this is Dr. Kraus with part 5 of the Bode series. I'm going to talk about my random Bode problem generator. This is code that should be on my YouTube GitHub repository for sharing code with YouTube viewers. So it should be available to anybody who has access to GitHub. Kind of the big idea is that if you really did just do a random transfer function, I think that might not be very helpful from a pedagogical point of view. It might not be very instructive. And so I've tried to write code that does an intelligent random transfer function generation. And you can use this to study for Bode related problems or learn Bode in two ways. You could generate a transfer function, show yourself that transfer function, say sketch this, or you could generate a random transfer function, show yourself the Bode without looking at the transfer function, and then trying to determine the transfer function first. So the way that the intelligent random transfer function generation works, I just don't think it's helpful if you've got a lot of poles and zeros on top of one another when someone is first trying to learn Bode analysis or Bode system ID or whatever. And so I divide the frequency range into a certain number of bins. Like I said in an earlier video, I think it's just, especially early on when you're trying to learn stuff, it's more helpful if the poles and zeros are well spaced. And so I divide the frequency range into a certain number of bins, and then each bin can only have one of 5 cases going on. It could have a first order pole, it could have a second order pole, it could have a first order zero, it could have a second order zero, or it could randomly have nothing. And so it's one of those 5 things for every bin. So you can't have poles and zeros in the same bin. You can't have any third order things going on inside of a bin, and so on. And just for causality purposes and my sanity, the number of zeros should be less than the number of poles. Now, randomly generated stuff, you obviously can't test that extensively because it's random every time, and so sometimes there are some glitches, but this is what it's supposed to do. And if you are testing my code and you come up with something and say, hey, this weird thing happened, then try to get me as much information as possible. We'll see if we can figure out how it happened and how to make sure it doesn't happen again. So as I mentioned, 2 options. Option 1, Bode sketching problem. So you generate a random transfer function. You show yourself that transfer function. Optionally, you can show yourself the poles and the zeros explicitly if you think that your instructor is generally a nice person and would do that for you. Then you sketch the Bode plot. You do not yet let Python generate that Bode plot for you. You sketch it, and then you let Python generate it after you've completed your sketch as a way to check your answer. Case 2, you generate a random transfer function, but do not look at the transfer function itself. Instead, you let Python generate the Bode plot immediately. You then look at that Bode plot and figure out where the poles and the zeros are and come up with an expression for the transfer function. And when you're done, ask Python to show you the transfer function and the poles and the zeros. So let's do a quick demo of this. Again, this is code that is on my GitHub under my YouTube code share, whatever. So I got to import kind of the normal stuff. And I have all my weird helper functions at the top that do the Bode generation and generate a list of poles and a list of zeros and turn that into a numerator and a denominator and ultimately. So this does assume that you have the Python control module installed. So a little bit of the same information here as to how to use this. So for example, in case 1, I generate a random transfer function. And the optional argument here is the maximum number of poles allowed. It defaults to 5. I've restricted it to 4 in this particular example. And then there's the transfer function, generate the Bode plot. That is a little bit messy. So I would expect my students to know how to use the quadratic formula, so they should be able to find the roots of the numerator and determine if that's 2 first order zeros or 1 underdamped second order zero, find zeta and omega n, so on and so forth. This is 4th order, so I wouldn't expect, even if you do factor out the s, so there's obviously a pure integrator. That still leaves you with a cubic. And so I would allow my students to either use a calculator or I would give it to them in a factored form. So then if you just use the pole and zero methods or functions or whatever, those are obviously negative because it's stable, and those are in radians per second. So pure integrator, first order pole, underdamped second order pole, and apparently that's an underdamped second order 0. So you would go through, you would sketch the Bode plot based on this information, first order integrator, so on and so forth. And then when you're done, you would check your answer by asking Python to generate that Bode plot for you. And so this is what you were supposed to come up with on your own. So pure integrator, underdamped second order pole first, or was it? Yeah, I think magnitude-wise, that's an underdamped second order, and then another first order pole, and then the underdamped second order 0 is last. So pure integrator, underdamped first order, sorry, underdamped second order. There's no such thing as an underdamped first order. Underdamped second order, followed by first order, and then underdamped second order zeros. So that is option 1, showing the transfer function, sketching the Bode plot by hand, and then checking the Bode plot when you're done. Option 2, you generate a random Bode plot, but you don't look at the transfer function. You just say, well, that's the answer to a different one. So that's not the current answer, and that's also one that wasn't supposed to be possible. Okay, so here is my Bode plot, and then I would look at this and say, okay, pure integrator, this drops down more than 90, so this is an underdamped second order pole, and then this comes back up 90, so that's a first order 0. And so then you would go in and find the actual numbers, so on and so forth, and there it is. First order 0, pure integrator, because I can factor out an S, and so my poles are underdamped second order and pure integrator, and my 0 is first order. So that's it. And then every time you want to, you don't have to re-execute this code once you've executed it once. Every time you want to generate a new problem, come back to here and eventually maybe make that go away. So now it's possible to have fifth order stuff, although, good golly, so that shouldn't be possible. There's a pure double integrator, but still 5 more poles. I'll have to look into why that was possible. That shouldn't have been possible. And then there's the pole list, there's the 0 list, generate the Bode plot, and then ask Python to generate it for you, and Python doesn't care how many, so that's a wacky 7th order deal. Pure double integrator, underdamped second order pole, underdamped second order 0, first order pole, underdamped second order pole. That's awesome. And so you could just keep generating those problems over and over again. And similarly, I could allow for up to 5 poles. Here's the Bode plot. Find the corresponding transfer. And again, if you're just getting started and you want to make life easy on yourself, you could say, I'm only willing to go up to 3 poles. Here's an easier problem. And again, that shouldn't be possible. I have to look into why that happens. So it is what it is. But this will generate for you an infinite number of random problems for either system identification or Bode sketching, though there seem to be some issues with limiting it to 5 fifth order poles and not allowing for improper transfer functions. I'll have to see if I can figure out those things. Thanks.